Hi friends, and good morning to one and all. Myself, Devala Lakshmi Narasimha Sai Jishnu from CSC Data Science B section. Today, I will be discussing about advances in polymer integrated optics. Next slide. The introduction of advances in polymer integrated optics. The recent surge in demand for photonic components that meet economic criteria as well as technical requirements in the telecom and data telecom industries has opened the door for novel technologies that enable unique functions and or unconventional high yield manufacturing without sacrificing high performance. Advanced planar polymer technologies can fit the bill in every aspect. Today, glass optical fibers are routinely used for high-speed data transfers, although these fibers provide a convenient mean for carrying optical information over a long distances. They are inconvenient for complex high-density circuitry. In addition to being fragile, glass fibers devices are difficult to fabricate, especially when they have high port count and as a result are quite expensive. Polymeric materials permit the mass production of low cost, high port count photonic circuits in parallel on a planar substrate. In addition, they provide the possibility for much higher degree of ruggedness. Work carried out in a number of laboratories has demonstrated these advantages. What has been needed in development and characterization of suitable polymeric material? Development of high-yield manufacturing techniques for polymeric photonic devices and full characterization of these resulting optical circuits. Each of the polymer systems available today has unique set of properties that make it suitable for specific communication applications. Materials that are used in advanced integrated polymer optics. Optical polymers were engineered in many laboratories worldwide, and some are available commercially. Classes of polymers for use in integrated optics include acrylides, polyamides, and of olefins. Companies that develop such polymer include Allied Signal. They are Amoco, Dow Chemical, DuPont, General Electrical, Hoscade Selenes, JDS Uniphase Photonics. Table This table lists the key properties of polymers developed at these companies. Allied Signal has developed a worldwide variety of photochemical set optically transparent polymers which are based on combinations of multifunctionality arclite monomers and polymers together with various additives. These polymers are particularly suitable for low loss optical devices because arclights intrinsically have relatively low strip optic coefficients and because photochemical processing directly from monomers provide low stress optic coefficients and because of photochemical processing polymers characterized by relatively low internal stress. These combination of material properties allows the creation of waveguide that exhibit both scattering losses and low polarization depend losses upon exposure to actinic radiation. These monomer systems from highly cross-linked networks which exhibit low intrinsic absorption in the wavelength range extending from 400 to 1600 nm. By bleeding and copolymerization, selected miscible monomers. The synthetic scheme allows for precise tailoring of refractive index over a very broad range for 1.3 to 1.6. This control of refractive index allows us to fabricate step index of or graded index optical waveguide structures with well-defined and reproducible refractive indexes differences to within 0.001. At the same time, the synthetic scheme allows other physical properties of the material such as flexibility and toughness, as well as such important properties of the same energy and adhesion to be tailored to meet the needs of specific applications. These materials have already passed much of the Belcore protocols 1209 and 1221. Key materials tests and characterized are discussed. Key properties of optical polymers developed worldwide. This is the table for key properties. Manufacturer, polymer type, patterning techniques, optical loss, other properties. As shown. First one, optical loss. The results of spectrometric studies performed in a set of arc lights are shown in figure. The figure is in the right side of the PPT. Notable features in the figure are the region of transparency around the datacom computing wavelength 840 nanometer. The CH vibrational overtones, which are most pronounced beyond 1 meter, and the windows of transparency near 1.3 and 1.5 meters. The wavelengths of interest for telecom optical absorption is in polymer materials is determined both by the energies of molecular or polymeric electronic excited both excited states and by the location of fundamental and electronic overtone vibrational excitations of covalently bond nuclei such as carbon and hydrogen. The location of these vibrational states is determined largely by the spring constant of the bond and reduce the mass of two nuclei. However, the loss measurements were also performed on channel waveguides using the Cleve Black method. These results of the study on multi-mode and single-mode two-dimensionally confining guides produced in our full CH content arc lights reveal average loss values at 840 Newton nanometer of 0.02 and 0.036 decibels per centimeter in the multi-mode and single-mode cases respectively, indicating that the loss achieved in waveguides can closely approach absorption's limited values when fabrication techniques are optimized. Next slide. Thermal stability, a key characteristic for practical application in thermal stability of our optical properties since organic materials may be subjected to yellowing upon thermal again. Typically, such again results from the formation of partially conjugated molecular groups characterized by broad ultraviolet absorption bands which tail off intensity through the visible. This yellowing is strongly influenced by the chemical structure of original polymer, although the aligned signal polymer systems described here are archaic. The chemical characteristics of various backbone segments can vary substantially from for example, simply aliphatic to aromatic and from either to ester to urethane. The choice of these linkages and monomers or oligomers ultimately determine to desuffi- um, designificant degree the characteristics of resulting polymer including surface energy, hardness, toughness, and modulus water uptake and stability toward againing. Because of their highly cross-linked nature, polymers derived from multifunctional alkylates are quite thermally stable. Thermally stability of waveguides material was studied by A variety of techniques including thermal gravimetric analysis (TGA), isothermal (TGA), spectrophotometry, and in situ optical loss measurements shows the TGA curves of non-halogenated core polymer. The thermal decomposition temperatures defined as the 5% weight loss temperature at a hearing rate of 10 coulombs per minute are 365 and 415 centigrade in air and in nitrogen, respectively. However, much important is the retention of high optical transmission upon thermal again. Thermal colorization is common problem with organic polymers when exposed to elevated temperature and must be minimized for applications as optic materials. This coloration is not always accompanied by white loss but causes increased optical loss. In order to investigate the phenomena, loss measurements at 840 nm were carried out. 5 centimeter long fiber pig- uh, pigtailed straight waveguides made with our non-halogenated polymers. This is the formula for non-halogenated polymers. A minus expenditure of minus E by A by KT. Next slide. Humidity resistance. Non-halogenated polymers were subjected to humidity cycling test. A sample was prepared on flat glass substrate. Multimode 90 in plain bends were produced. These guides were 100 m in cross section and 10.9 centimeters long. The present observation also give no evidence of mechanical failure of devices due to water incursion such as delamination or loss of integrity at the interface with the glass fibers. The fact that humidity has very little effect on these polymers was expected. When fully cured, these materials have very high level of cross-linking, resulting in tightly bond network with low level of voids, leaving little space of water to be absorbed. Halogenated polymers were found to be even more hydrophobic. Fourth property, temperature dependence of refractive index. A key difference between polymeric materials and more conventional optical materials such as glass is that their refractive index varies from more rapidly with temperature. This large difference in can be leveraged to produce efficient thermophotically active optical components. The value of different classes of halogenated and non-halogenated cross-linked arc-light polymers varies between about -2 and -3 into 10 by centigrade, when the large magnitude dN by dt is not desirable. Passive compensation schemes can be utilized as well as discussed later in the content of stability of grating based filters. Fifth property, humidity dependence of refractive index. The refractive index was measured to have a low humidity dependence for non-halogenated arc lights per percent RH and more than order of magnitude less for 80% halogenated polymers. These effect on guide performance in minimal sense core and cladding materials undergo similar variations. Refractive index dispersion. Many optical systems rely on having non-wavelength dependent optical effects other than those geometrically designed into systems. Therefore, material dispersion is generally to be avoided. These refractive index of several polymers and a standard material SiO were measured at various wavelengths in order to obtain wavelengths. Results at key communication wavelengths were shown for non-halogenated core and cladding polymers and the standard SiO. Polarization and dependent loss. Another important property affecting polarization transparency of optical component is the PDL. The PDL value, which is equal to loss, varies that with processing conditions. The TE loss measured in our single mode waveguide is typically slightly higher than the TM loss, mostly due to the fact that where vertically walls of the core have slightly more roughness than the horizontal boundaries measured performed on single mode waveguides at 15 nm reveal that PDL in waveguides can be reduced below 0.01 decibel per centimeter, and the value at interface can be below 0.01 decibel per interface. Mechanical flexibility and material toughness. This is a uh, to improve toughness and reduce stress, we designed optical polymers on the basis known structure property group additive relationships for prospective organic polymer segments. Applications. First one, telecom. Polymer components produce the telecom industry signal, single mode splitters, couplers, rotors, filters, and switches. One of these earlier drivers for the work with polymer waveguide was concept of fiber to the home, which raises the possible future need for low cost passive optical components such as splitters. Second application of advances polymer integrate datacom. Recent advances that have continued to propel optical interconnects as the wideband technology of choice in datacom include vertical cavity surface emitting laser VC, VCSEL sources. VCSEL packaging polymer-based optical waveguide and fiber materials, low-cost micropolygon components, passive alignment, low-cost connectors, low-cost fabrication processes. Technologies have high level of similarity. The development of polymer interconnect technology for datacom applications was carried out by Allied Signal for both internal aerospace application and under DARPA sponsored programs. The Point program developed high-speed optical interconnects employing the polymer waveguides. A natural role of low loss polymer interconnects is computing cabinets in the where run lengths can be large in where state of art polymer values are need to be produced desired long wavelengths while keeping total insertion low loss. Next slide. Conclusion. We have revived the key properties of polymeric systems developed worldwide for the telecom and datacom industries and have given a detailed description of allied signal cross-linked alkylate photopolymer waveguide technology. These materials are characterized by low optic loss, thermal stability, humidity resistant, low refractive index depression, low PDL, low brief currents, flexibility, mechanical robustness, high photolithographic constant capability of precise tailoring of the refractive index and ability to cast a wide range of contra thickness. These unique materials properly enabled fabrication of variety of optical waveguide devices, such as straight waveguides, bends, splitters, directional couplers, MMI couplers, star couplers, wavelength filters, and long high-density waveguide arrays. Structures were produced by conventional mask photolithography at adaptive laser writing, soft embossing, and their adhesion to variety of rigid flexible substrate were demonstrated. This combination of conventional lithography manufacture and broad range of advanced specialty polymers indicate the potential of this technology to be solution to the problem cost effective production and of high performance integrated optical creativity. Thanks for giving this golden opportunity.